Morning, everyone. So yesterday we introduced how alkyl halides react. They undergo something called nucleophilic substitution. A nucleophile is something that is very electron rich and it wants to attack something that's positive. We found that the substitution could actually take place via either an Sn2 or an Sn1 mechanism. I'm just going to ask you a quick question to practice in Sn1 with you. And then today in our lesson, we're going to talk about what are some of those features towards the end of yesterday's lesson that would decide whether it's more likely Sn1 or Sn2. At the end of the day, it's probably going to be some combination, but we can at least make some guesses and some predictions in which one is it more likely to be. So I'm just going to practice your question with you. Again, good practice for yourself is see if you can sketch out a mind map for yourself. We've done basically 90% of the reactions that we're going to look at. We can now actually interconvert between one family to the other family. So I'm going to practice this one right here with you here for a mind map. We started off looking at alkanes. So alkanes, relatively boring because alkanes have really strong carbon-carbon bonds, carbon-hydrogen bonds here. These ones only high energy sources. So let's say combustion reaction, we can get combustion products, or under the presence of UV light, with Cl2 or Br2, they can also undergo a substitution. That one there is not nucleophilic substitution. That one there is through a free radical mechanism. That ends up forming an halogenoalkane or a alkyl halide. Either way is fine. We started seeing alkenes were a lot more interesting. Alkenes have a carbon-carbon double bond, and we can actually undergo electrophilic addition. We can add electrophiles across the double bond. First thing that we did is we wanted to convert alkenes back into alkanes. That process was called hydrogenation. I'm going to actually add a hydrogen across the double bond. That one needed a catalyst, and it needed slightly hotter than room temperature. So typically we use nickel as a catalyst. I usually quote 150 degrees. It's not a magic number. You can say 160. It doesn't really matter. Okay, but some are hotter than room temperature. So that's hydrogenation here. For the alkene, we can also add an HX. So if HX is the chemical here, this can take place at room temperature. The X there would be your chloro, bromo, or iodo. We can end up substituting the alkyl halide. That's a good test between alkane and alkene. Alkanes will only react if there's a UV source, whereas the halides can add. The substitution can happen even without a UV source. Alkenes can end up forming a dihalogenalkane. So if I actually add the whole dihalogenalkane, so if I add just an X squared, so Cl2, Br2, that also occurs at room temperature, so that just adds across the double bond. We found alkenes with other alkenes like it. They can end up forming polymers. They end up repeating N times. A lot of plastics and nylons are actually polymers. It's the same monomer repeating unit that goes again and again. Most important here was this is an equilibrium reaction with concentrated sulfuric acid as our catalyst. Water is the ingredient that we're trying to add. We're going to end up forming an alcohol family. Okay. Alcohols have a characteristic OH. Alcohols will also burn in O2. Alkenes will also burn in O2. No problem. Okay. Alcohols, usually we use some oxidizing agent. Very commonly, we use acidified dichromate. It's a little bit more mild than potassium permanganate. It converts from orange to a green color. And then for this one, depending on whether it's first degree, second degree, or third degree, the outcome is different. Third degree here is always going to be no reaction. Second degree here, usually with heat and reflux or heat and distillation, we're going to end up getting a ketone. Right? There's no sort of middle product here. Ketone is another family. For primary here, if I do heat and distillation, if I pull off the sort of temporary product here, distillation ends up forming an aldehyde, whereas if I just heat it and I completely reflux it, I just completely finish the reaction, full extent of equation, this will end up forming a carboxylic acid. Okay, so we know how to convert sort of many families to many families here. Yesterday when we started doing nucleophilic substitution, we're starting way over on the right-hand side. And on the right-hand side here, we started seeing a few different nucleophiles. When we add an OH to substitute the place, imagine this one here is a CX like this. If an OH replaces the halogen group, it's just an alkane left with the OH group. Well, that's an alcohol. So this part gets a little bit messy here. Maybe use a different color. I can actually get from halogen alkane to an alcohol by reacting with hydroxide. That's going to be our nucleophile. There were other nucleophiles that we did, so we can add in, let's say, a ammonia group or an amine group. That's going to end up forming for us an amine. We can add in a cyanide group, a cyano. This one here will end up forming a carbon nitrile. So those are two other families here. After we talk about Sn1 and Sn2 early in this lesson here, decide which one is more common, we're going to do one more cross combination here. What if an amine reacts with a carboxylic acid, and what if an alcohol reacts with carboxylic acid? So again, some more interconversions. Hopefully by drawing this mind map here, it'll help you sort of keep clear of this. Okay. So let me do the one reaction for you, just practicing Sn1, Sn2 again. This question here was on your package there. 1 bromobutane. I want you to react this one here with potassium hydroxide. Okay. Earlier they had done it using an Sn2 mechanism. I want you to show it, what would this look like using an Sn1 mechanism? Just to change things up a little bit. Okay. So we had done this one. Let's start out drawing our butane, 4-carbon parent. On position 1, we have a bromo group. Because we're worried about stereochemistry inversion, I might need to have hydrogens, right? We'll see what happens. Potassium hydroxide, I don't really care about the KOH part. The K plus is just spectator. I just care OH minus in solution, and that's going to be a nucleophile. So I have an alkyl halide and I have a nucleophile. What's going to happen here is it's the polarity of the C-Br bond that's actually potentially going to react. So what I do here is I just resketch this out here. I go carbon with the bromine. Sure, you can still have these hydrogens here. The part that I'm going to condense is actually this part. I don't want to have to always draw that 3 carbons in a row. I'm just going to say C3H7. Again, it's the polar bond that actually makes you susceptible to attack. The more polar you are, the more positive ending it is. Bromine is actually not that electronegative. The partial positive is not going to be that great. But nonetheless, the OH minus, it's so electron rich, it's going to donate its lone pair to attack the carbon. This bond here heterolytically fizzes and actually goes back to the bromine side. I need to show you the mechanism. So Sn1 is the mechanism. Before the nucleophile is even present, step 1, okay? So step 1 actually involves just taking this guy here, and the halide just up and leaves. So we had carbon, bromine, I'm just going to copy this out here. Hydrogen, hydrogen, and my C3H7. My bromide, being a polar bond here, it just up and leaves. This is a relatively slow step. So I'm going to have bromide, that's going to be Br minus, and I'm going to have formed a carbocation intermediate. C3H7, whenever carbon is bonded to just 3 other electron domains here, we've formed a trigonal planar. We've been calling this one here a 3-coordinate, you can say trigonal planar, and that's for 3, trigonal planar intermediate, as opposed to Sn2, which was a 5-coordinate. All 5 things are all present at the same time, all in the same spot in space, all colliding with good energy, good geometry. This one here being planar, that was step 1. Step 2, right, again, don't get confused. They do call it Sn1. The Sn1 talks about in the first reaction, the rate law only depends on the halide. So that's why it's the 1. But this actually takes place in 2 steps. As my hydroxyl group comes in, hydroxide can either attack above or below, resulting in 2 potential products here. We can have, let's say the OH has attacked from on top. We're going to have carbon, the C3H7, and then we still have the hydrogen group and the hydrogen group back that way. Or the OH could have attacked from the bottom. Carbon, OH, again it has the C3H7 group, and again we have our hydrogen and hydrogen. This one is not a chiral carbon because it's not carbon bonded to 4 other neighbors, so these 2 are actually identical. But if there was actually RS here, they would probably be enantiomers of each other. Okay, we'd be now forming a racemic mixture, a 50-50 mix of the S type and the R type. So let's just label some of these terms here. We call the guy coming in our nucleophile. It's liking of electrons. The leaving group is the Br minus, depending on the stability at which this one here has in solution. You can generally find it experimentally. That's going to say how easy this bromine just up and leaves. And then because we are just planar in step 1, we can actually attack from both sides, something we couldn't do in the Sn2 mechanism. Okay? So today I just want to flesh it out a little bit more here. How do we know whether it undergoes an Sn1, Sn2? What are some of these features that I need to worry about? So let's compare Sn1 and Sn2. Afterwards, we're going to look at a condensation reaction. Okay? So comparing an Sn1 and Sn2, you'll notice both of them are nucleophilic substitutions. The one tells you this is unimolecular. It tells you that in step 1, it only depends on the halide. The 2 actually tells you bimolecular. The thing that is really confusing is the Sn1 is actually 2 steps, while the Sn2 is actually 1 concerted step, one thing all at once. So, wait a second. 2 mechanisms for the same reaction? How do I know which one is going to occur? Yesterday, we ended off with the phrase here, Sn1 generally are faster than Sn2, even though relatively speaking, step 1, it's not common for the halide to just up and leave. Here, comparing Sn1 against Sn2, usually if something is a primary alkyl halide, if it's carbon attached to one other carbon, usually these ones here react via an Sn2 mechanism, while a tertiary typically reacts using an Sn1. We're going to talk about 2 reasons why this is. Secondary can react via both mechanisms, so some combination of the 2. Remember, we end up getting the same chemical reaction. It's just if I could dive into the details and figure out, did it all happen all at once or not all at once here? It's just the mechanism that we're interested in. Okay, so there's 2 features here. First feature that they talk about is steric strain. Sometimes they also refer to it as steric hindrance. Steric just refers to are there any blocking groups? Because especially as this reaction is trying to occur, I need the nucleophile to actually have access to the carbon. If the carbon is actually surrounded by a whole bunch of other groups here that actually make it hard for me to actually attack the carbon, I'm going to have less of an incentive to attack the carbon. So, steric strain here is repulsive interactions that occur when the atoms get too close for contact. So, what we have here, we have a primary carbocation. We just said primary typically occurs in Sn2. So, let's remember what an Sn2 reaction was. An Sn2 reaction was our nucleophile. I'm just going to N here. Our nucleophile, this is actually NU, so it doesn't look like nitrogen. So our nucleophile is very electron rich here. The nucleophile has to attack this carbon center. Think about geometrically what it needs to do. It's just randomly colliding and going any which way here. The nucleophile has to hit this carbon. Nicely, this carbon being a primary alkyl halide, it has a small hydrogen group, it only has one methyl group that's slightly larger. It's still fairly easy for you to have access to that carbon. Let's compare it to the opposite one here. This one here is actually a tertiary carbocation. So same reaction, it's the polarity of the carbon-bromine bond that wants to bring the nucleophile in, but these ones here sort of act like almost like tumors here. Instead of hydrogens being tiny groups here, we have a methyl group. From earlier, it was fairly large. Then I have an ethyl group here. That's a really big group. Then a propyl group here. This one here has side attachments, all at sort of 109.7 degrees. For the nucleophile to come in, while it's not impossible, it's going to have a hard time running in between, squeezing between these neighbors here to try to have access to that carbon here. So we'll just write this down here. For a primary alkyl halide, even if I could get rid of that methyl group even better, it's still going to be primary. Primary alkyl halides have little, or have none, have little bulky side chains. At best, it's only going to have one bulky side chain, but still the hydrogens are still fairly narrow. I can pretty much squeeze myself between the 2 hydrogens. So therefore, it has a low steric hindrance. The stereochemistry, the 3D angles at which this thing here is trying to come in at here, it's not really blocked by those groups there. And because there's not a lot of blocking, so therefore, I can actually attack fairly easy. So, therefore, less blocking means the nucleophile easily attacks the carbon-bromine, the carbon side, the partial positive on that C. Okay. Whereas when I had those 3 groups here, you can see, well, such bulky side chains here, such bulky groups here, it's really hard for me to weave myself in there. Not impossible, but if I had a different mechanism, I would prefer that mechanism. Okay. Inductive effects here. We already saw especially positive inductive effects. For positive inductive effects here, we can compare, I don't know why they gave the picture twice, but we can compare here the inductive effects here, especially when we're talking about carbocations. Remember, carbocations, these are positive carbons. Carbocations are unstable. Carbons shouldn't have a positive charge. But depending on how many alkyl groups, depending on how many other carbon groups there are, this can actually form more stable intermediates or not as stable. We saw this briefly using Markovnikov's rule here. Sometimes when you added an alkyl halide across a double bond, we end up forming a carbon on one side temporarily. The carbon, if it's surrounded, this one here is a primary carbocation, it only has one carbon group that has inductive effects that can push some of its electron ability to try to stabilize that positive bit. Versus a tertiary one, if I have a tertiary carbocation, I have three groups. Although all groups that are neutral, they can't get rid of my positive charge, they can actually positively induce here. There's actually greater, for tertiary, greater inductive effects. So therefore, we have more stability. So while earlier we were referring to, well, how about the carbon groups here? They're bulky and they're making it hard for the nucleophile to attack. If I want to undergo a mechanism that uses a carbocation, namely an Sn1 mechanism, if I want an Sn1 mechanism, I actually do want those bulky side chains, because the more carbon chains that I have, it's going to actually stabilize the positive. It's going to allow my leaving group to actually go away a little bit earlier. And now that I'm actually flat, now I don't really care about the bulkiness. Now my nucleophile can actually come in, attack from one side or attack from the other side. So that's typically the distinction that we end up having. Primary alkyl halides, primary ones here, they don't have many side chains here. The nucleophile can attack much more easy than, say, a tertiary. For an Sn1 mechanism, which actually needs a carbocation intermediate, the primary is not so good. I would have been flat either way. I could have attacked either way, but primary only has one carbocation inductively donating its electron density. So I actually want to have the tertiary, and in that case, because based on being flat anyways, then my nucleophile is the second step. That's why it's such a fast step anyways. It can attack from either side. So let me just write this down for you here. We talked about here the tertiary carbocation here is much more stable. The tertiary carbocation is not only more stable, is more stable and flat, allowing, where earlier we were saying the nucleophile had a hard time coming into attack, allowing the nucleophile to attack from either side. If I undergo an Sn1 mechanism, if it would have been two steps anyways, just the leaving group just up and leaves, I don't really worry about the side chains anymore. So your bulky side chains, that's a bulky group, this is a bulky group, even this is a bulky group, but this one here is now a flat piece of paper. The nucleophile can easily attack from one side or the other side there. Okay, so just in conclusion there is, although these are both potential mechanisms where the halide can get substituted, if something is primary, I say Sn2. If something is tertiary, I say Sn1. A secondary one will have sort of a little bit of both. It sort of has some bulky side chains, makes it a little bit harder, but it only has a secondary carbocation, not quite as good for an Sn1 mechanism. Usually it's going to have both. Okay. I want to introduce one other feature here as you start talking about, well, what does this rate here depend on? We can also introduce what I refer to as solvent effects. So far, we've just been under the assumption, well, this just takes place in water, right? Water is the background, we're in aqueous and all this. It turns out you can actually control or select for either Sn1 or Sn2 depending on what solvent you actually use. An Sn2 reaction is actually going to require a polar solvent. I'm going to introduce a word here. We would prefer an aprotic solvent. Okay, that word aprotic, A means without. Without protons actually refers to there's no OHs, or there's no like NHs. And if you're looking closely here, well, what's the big deal? What if I had OH, or what if I have NH like this? These ones here actually have hydrogen bonding. We're going to see in a second, well, why that's the case. So Sn2, I want to have a polar aprotic solvent. I can give you some examples of them there, like propanone. Okay, can draw you the structure here. Propanone here is actually, well, we have 3 carbons here, we have a double bond like this. We do have polarity that hits my polar, but we only have dipole-dipole forces. We don't have hydrogen bonding. Or we can have ethane nitrile. So nitriles are good for these aprotic solvents as well. Ethane nitrile, so if I had carbon, and nitrogen like this, yes, we will have some polarity, right? The carbon loses to the nitrogen, but again, no hydrogen bonding, just dipole-dipole. So if you want to choose a solvent to select either for Sn2 or Sn1, choose a polar aprotic one. I'm going to give you the Sn1 as well, and then tell you why this is the case. For an Sn1, we also want polar, so that's in common for both, but polar, the difference is we actually want a protic solvent. Usually a lot easier. These ones here can contain OHs, can be water, can be ammonia, no problem. NH kind of bonds here, no problem. With the examples there, the examples could be just plain old water, or it can be ammonia. Okay. Let's just do a quick note here. Well, why is this the case? Why was it that I really didn't want hydrogen bonding for Sn2, but I'm okay with hydrogen bonding for Sn1? What I want to do first is just the similarity. Okay, both of them need polar. Why is that important? If you look at an Sn2 mechanism, you need your nucleophile to attack the carbon. I'm going to have just some R groups here, R prime, R double prime. I need to have a 5-coordinate state here. So we have a transition state where all 5 things are present. If the Sn2 solvent actually has hydrogen bonding, what's going to happen is, let's say it's water as an argument's sake here. Water is actually going to start surrounding this nucleophile, actually impeding the nucleophile's ability in actually reacting. So in the rate law, we would say the rate law for a Sn2 mechanism, it depended on your nucleophile and it depended on your halide. Well, now that water has actually tied up your nucleophile, water is actually so good, it doesn't have any preference, only hydrogen bond with some people. It can actually hydrogen bond with nucleophile. Let's actually write that down here. Water interferes with the nucleophile by hydrogen bonding. So it allows less nucleophile to actually attack all in one step. Now what about an Sn1 mechanism? An Sn1 mechanism, the slow step, it only depended on the halide. So K times Cx like this. So we had our alkyl halide, so C with R, R prime, R double prime like this, and then we have an X group like this. Remember step 1. Step 1 is just we end up forming a carbocation intermediate. We just talked about there being those inductive effects here. You notice step 1 has nothing to do with the nucleophile. In fact, actually, the reason why both of them wanted to be polar was, oh, now I actually have a carbocation. Water is actually something that can hydrogen bond. Water can actually help to stabilize. I'm not talking about sort of the attachment here, actually switching off. I'm just saying water can actually surround this carbocation and actually help to stabilize your carbocation intermediate. So water with hydrogen bonding, water can help stabilize the carbocation intermediate. Okay. So definitely you do need to be comfortable with both Sn1 and Sn2 type reactions. You need to be able to decide whether you expect it to be Sn1 or Sn2. And so far we looked at a few different features. We've looked at the solvent. We've looked at how many sort of side groups you have, the stability of the carbocation chain here. What I was alluding to last day, I want to just touch on it some more as well. There's a lot of factors that sort of interplay here. We actually want the bond to be more polar. So if I compare a C to Cl, a C to Br, a C to I bond, the C to Cl bond is most polar. This carbon here is going to be most positive, most negative. These ones here are going to be much smaller for polarity. So if a nucleophile were to attack, the nucleophile would tend to like the side that's more positive than just this side here. So usually for polarity, we want a higher En difference. Right? However, we also need to consider the bond strength here. Well, this bond here has to up and leave. The chlorine has to actually leave here. Turns out, if you actually look at bond enthalpy values here, the bond enthalpy, bond strength, actually decreases going down this way. And it turns out experimentally, these are sort of two competing things. In the one hand, I want it more polar, so the nucleophile wants to attack it, but unfortunately this bond here is stronger than the Ci bond. Turns out experimentally the bond strength feature is more important. So therefore, just in terms of rate, just a qualitative thing, if everything else is equal, we're going to find that substitution on a Ci is actually faster than a CBr, is actually faster than a CCl. Because of bond strength here, the Ci bond is actually the weakest bond. So although it may not be the most polar bond, although it's not the one that the nucleophile necessarily wanted to attack first, because this bond here is actually the weakest, this one can up and leave the easiest. We also alluded to experimentally, I- is also more stable as a leaving group. So what I want to just introduce to you in this section here is there's a lot of factors that come into play. The leaving group, the bond strength, the polarity, the solvent, the attachments. All of those things here have to be factored in to decide whether you are Sn1 or Sn2 for the substitution to happen. Okay. So hopefully that clears up a few things for you for Sn1, Sn2. We're just going to finish off with a really small section here. One last type of reaction that we're looking at is going to be called the condensation reactions. The reactions we've been investigating so far has reacted one thing that's organic with something that's non-organic. So sort of two things, seeing the conversions. So far we've done two types. One is overall being called the addition reaction. Addition reaction we saw with alkenes. So let's say I have ethene here. I can add a Br2, halogen across this one here. This forms a dihalogen alkane. An addition reaction involves two things becoming one thing. It's like a fancy synthesis kind of reaction. We just did Sn1, Sn2. These ones here are referred to as substitution. We did nucleophilic substitution. So the nucleophile comes in and swaps its place for the leaving group. This one here, perhaps we have a nucleophile. And then we have a CH3. It's that bond with the X that we care about here. The nucleophile here can actually attack the partial positive side of the carbon. The leaving group ups and leaves. Being a substitution, we had two things ending up having two things at the end. So nucleophile still with CH3, and then an X group as the leaving group. So two things becoming two things. Now what we're going to do is another main type of reaction is referred to as condensation reaction. Condensation usually, you can make a note to yourself, usually removes water. Right? So we're going to be pulling out a small group, and we're actually going to be attaching two groups together. So this part here is just a very small section. We don't need to actually know the mechanism for this. Let's take a look at, let's take two organic molecules and actually forming one thing. So two bubbles on my mind map and actually attaching them together. This first reaction is referred to as an esterification. We are actually making an ester. Well, what is an ester made up of? It's actually made up of a carboxylic acid. We had produced a carboxylic acid from oxidizing a primary alcohol and reacting it with an alcohol again. So one alcohol fully oxidized and then reacting with alcohol again. Essentially what ends up happening, again, the reacting conditions are important. We need concentrated sulfuric acid as our catalyst. We needed a little bit of heat treatment, so try and go for heat. And basically we end up getting a ester. So what ends up happening here is we actually, let me color code this for you. For your alcohol, we have an OH group. I'm going to color that in green. I'm going to color the H on the carboxylic acid in blue there. The water that we're going to end up releasing is actually that water there. So by condensing, by pulling off that water there, we end up having our carboxylic acid. So far they had a R prime, C double bond O. We still had the one O. I lost this H and the OH, and now I've glued the two R's together. The nice thing about this ester here is it is a functionality that comes sort of mid-chain. Aside from this one here, an ether was also one that did this. So that's a condensation reaction. An ester, by removing a water, we've glued the two parts together. In a very similar fashion here, we have what's referred to as amidation. So in making an amide very similarly takes a carboxylic acid, a fully oxidized form through reflux and whatnot. This one here reacts with amine. This one here can take place in more gentler conditions. It just needs a bit of heat treatment here. This one, there is a temporary step. I'm just going to show you this step. This step here, again, you don't need to know the mechanism of this one. This one temporarily ends up somewhere along the way, ends up forming a salt, right? Some ionic compound that ends up having sort of positives and negatives, and eventually what the heat treatment does, just continue to heat it, it eventually allows for the R prime to end up leaving you with an amide. So NRH like that. And in both cases, the similarity is we've done a condensation, it ended up releasing off of water, we ended up producing an amide. Right? So that's just another organic family for us. Why are they called condensation reactions here? Because a water is eliminated, a water is being released, or we can just say here it's produced as a product. Okay. Again, no mechanism needed for this here. You just need to note, how do we make an ester? Join a carboxylic acid with an alcohol. How do we make an amide? Join a carboxylic acid with an amine. Just memorize these reacting conditions. Okay. So these reactions can also occur in reverse. So there's an equilibrium sort of set up here. We call that hydrolysis. So water, using it to split this apart. Since we pulled away water to glue the parts together, I can actually add water and I can cause it to split up again. An ester was made out of carboxylic acid and alcohol. If I add the water back, I reform the alcohol and reform the carboxylic acid. So we can end up forming my carboxylic acid back, and I can have my alcohol back. Or by adding water to an amide, we can split it back into a carboxylic acid and also end up forming our amine product. Okay. Both condensation and hydrolysis are very often catalyzed by acid or base. The mechanism is very complex, way complicated than Sn1, Sn2. So all they're going to ask you to do is, if they give you an ester, if I add water, what are the two things that made it up? See if you can break it apart there. And let me just do the first one with you just for practice. We have methyl-ethanoate. It is already an ester. Remember, the alkyl branch is when you name it, this one here is the oxygen side. When we named esters, we had an ester functionality C110O like this. It didn't matter how many carbons there were, like which side was longer. The oxygen side was always the branch. That's methyl. Ethanoate here is the other side, so CH3 like that. Well, what would this have been formed from? I would actually need to add a water to end up sort of separate this here. And the way I think about it here is the H ends up sort of attaching to the carboxylic acid side, and the OH ends up attaching to the methanol. So therefore, if I just leave it color-coded for you here, we're going to have H3C. This is why it's reversible. O and an H. And then we have recreated our alcohol and our carboxylic acid. This one here, again, concentrated sulfuric acid for the reversibility. That's our catalyst. And then we have heat treatment. Okay. So you can try out a couple more of those here. Anytime you're given this, see if you can break it apart. What was this formed from? Right? If you have any questions, just let me know. Thanks, guys.